Okay, so welcome to Introduction to Parallel Computing on the HPC. This is another part of our summer workshop series. We've covered Intro to HPC on Monday, and we did an intro to machine learning using Python yesterday that Soham so nicely led. And today we're going to get into parallel computing on the HPC. And the HPC's power really comes from parallel computing. So this will hopefully help us take advantage of the HPC's power as we continue to learn more about it. So if there are any questions along the way, feel free to drop them in the chat. I have finally figured out how to look at the chat and do presenter view at the same time. So drop them in the chat and I'll see them. You can also feel free to just unmute yourself and ask a question. That's totally okay. I don't mind the interruption. So let's get into it. So here's a quick outline of what we're going to cover today. Section 1 will cover some background and theory. Section 2 will cover practical parallel computing on our HPC system. And for Section 3, I'll have some examples for you. Yeah. Hello? Okay. And Section 3 will be examples, including one Python multiprocessing and MPI for Pi example that I wrote up for us to look at on GitHub. And yeah, might as well just jump into it. So why do we care about parallel computing? If we look at the structure of a laptop versus the structure of a node on the HPC, we can see some differences. The very common MacBook, in fact, the one that I'm on right now, the M1 8-core, this has obviously 8 cores of CPUs. So that enables it to do some parallelization. The thing with using personal computers that have multiple cores is that oftentimes the programs that we're using on these computers just sort of automatically know how to use those cores, and it's not something that we ever really have to explicitly think about. Whereas this Penguin Altus XE2242 chassis is a compute node. This has 96 cores, so quite a lot more than the MacBook Pro. And this chassis, just to kind of compare what the hardware is, if you look at the MacBook, this is going to be high-end hardware that you have in here. The M1 chip is a very advanced chip that has all sorts of interesting features, such as unified memory and other things. And the chassis compute node that we see here, this is a bit less advanced in terms of the actual components themselves, but of course it wins out in terms of sheer scale, right? It has 96 cores rather than 8. Those 96 cores are cores that you might find in a mid-range sort of computer rather than the advanced cores that you find in the MacBook. And just by comparing the prices, you can kind of see that the price per core on the chassis is a lot less than the price per core on the MacBook. So that's just to sort of give you an idea of what the hardware that we're working with is. And then if you look at the cluster as a whole, the Puma cluster, for example, has 269 compute nodes with almost 26,000 cores in it. And this machine, of course, is very large, very expensive. And we will be learning how to take advantage of all of these resources that are available in this cluster. So in order to talk about parallel computing, we have to first talk about serial computing. And serial computing is more or less what it sounds like. You have a program that is broken down into a discrete series of instructions, and those instructions are executed sequentially on a single processor. So that's the key feature of serial computing, is that those instructions that the problem gets broken down into are all executed on a single processor in the exact order that you would expect them to be executed. and only one instruction can execute in each time step. So these are all very important features of serial computing. Parallel computing, on the other hand, is when the problem is divided into discrete parts that can be solved concurrently. So the important thing with parallel computing is that these steps are independent. If we have dependent steps, then we're going to have to execute them in order, as we see in serial computing. Whereas in parallel computing, if you have instructions that can be executed at the same time that are independent of one another, that's how we take advantage of multiple processors. So instructions from each section execute simultaneously on different processors. So this is why that's important. And of course, we need to employ some overall coordination method in order to make sure that we're solving the problem appropriately. So just to compare those two diagrams that we saw, we have serial computing, where the instructions are given in order to a single processor. We have parallel computing, where the instructions are broken into parallel segments that are fed into multiple processors. So the majority of standalone computers today are parallel from a hardware perspective, meaning they have multiple functional units, multiple execution units or cores, and multiple hardware threads. And here's a list of components of a CPU, if you're interested. So parallel computers can typically be built from cheap-ish commodity components because, again, the power of a parallel computer doesn't come from its clock speed or from its read-write speed or from its advanced caching system or anything like that. The power of a parallel computer comes from the fact that there are many CPUs that can all be accessed at the same time. So networks connect multiple standalone computers that we call nodes in order to make a larger parallel cluster. So this image that you see here is the rack layout of our Puma cluster. And each compute node is a multiprocessor parallel computer in and of itself. So there's multiple layers of networking that you have here. You have CPUs that are all interlinked within a particular node. Again, we have 96 of those CPUs per node in Puma, 94 of which are available in case you've ever run into that number. So 94 available CPUs on a node, but there are hundreds of nodes. So there's multiple layers of this interlinkage, and they're all connected via a high-speed network. There are also some special purpose nodes, such as GPU nodes and high memory nodes. So there's fewer of these because they are more specialized, but they do allow you to access other types of resources, such as graphical processing units or nodes that have a lot more RAM or memory available to them. So why do we use parallel computing in the first place? And the reason is that parallelization accommodates complexity. So in science, we're often interested in answering very complicated questions. And in order to have a model that accurately represents these complicated physical systems, well, we're going to need a powerful computer in order to accommodate all of that complexity at the same time. So natural processes can be accurately modeled with high resolution simulations or models. Oftentimes, these simulations or models have a large number of components or multiple types of components. There are oftentimes interactions between these components, and they evolve in a temporal sequence. So an example could be natural language processing models having billions of parameters. Or another example, my background, for example, is galaxy formation. So you have these simulations that have multiple types of components, they evolve in time steps, and they process a very large number of components each time. So you need a large number of CPUs in order to accommodate that model. If you try to run that on your personal computer, it's going to take until the end of the universe to run. So parallelization also decreases time to result. Tasks with a greater number of independent calculations will benefit from dividing the load between even more processors. So many hands makes for light work effectively, right? So working in parallel shortens completion time. And these are good examples that you see on the screen here because a lot of these tasks are independent. if I'm harvesting one row of a cornfield, it doesn't matter whether I harvest row 10 or row 11 first, right? What matters is how many corns I get in my basket at the end of it. So these are good examples for how the calculations are independent. So parallelization also provides concurrency because a single processor can only perform one operation at a time. In contrast, coordinating multiple processors allows for many operations to be performed in one single clock cycle. So an example of this is the shotgun technique that sequences a genome by breaking a long string of information into shorter segments and then to reassemble it. And parallelization also takes advantage of non-local resources. So in some sense, this means just the fact that the HPC is accessible remotely. And in another sense, it means that there are many HPC systems available throughout the country that researchers can use. So these enable users to have access to these powerful systems without having to manage the complex hardware themselves or to hire an IT person to manage that complex hardware for them. It allows access to powerful computing from anywhere with an internet connection. Distributed computing also allows for another level of meta parallelization. An example being this folding at home project, which is a distributed computing project to simulate protein dynamics. Distributed computing meaning that anybody with a computer can log on to this folding at home project and donate CPU time to it. So it'll, send the problem to your personal computer, and then you can run it. And naturally, HPCs are going to be a little bit more effective at this than personal computers. So actually, 3 public Arizona universities have supercomputers which have contributed to this project. So go look that up if you think that's an interesting thing. So now it's time to talk a little bit about parallel computing terminology to make sure we're all on the same page with the different words that we're using to describe these features. So let's start off with node, which is the most common component of a parallel computer. It's effectively just an individual computer. You could run on a single node, install your operating system, do everything you need to do just on one node. So it's sort of like the smallest operable unit of a parallel computer. Then when you start linking them together and having them communicate, now this is a supercomputer. A CPU is a component of the node, so it's a single socket or processor. It's a physical device mounted onto the motherboards. Puma nodes have 2 CPUs. And here's where some confusion comes in, because oftentimes the words CPU and core are used interchangeably, but from a hardware perspective, a CPU is actually sort of a step above a core in the sense that CPUs contain many cores. So the core is actually the component of the CPU, the smallest component that's capable of conducting independent work. So for example, Puma's CPUs have 48 cores. So if a node has 2 CPUs, each of those CPUs has 48 cores, therefore we have a node that has 96 cores. And oftentimes, when we're working with the system directly, we're using the Slurm interface, and Slurm so unhelpfully calls them the same thing. CPU and core refer to the same thing. So oftentimes, you'll find in a Slurm setting, you don't need to distinguish between CPU and core. So this is just something to be aware of. And you might find even in our documentation, we might use the term CPU and core interchangeably, because from a user perspective, it doesn't really matter how many cores are on a particular CPU, because the core is the thing that you're actually requesting and interfacing with when you are requesting a job. Okay, some more terminology on this page. So a process is a particular instance of a program with access to its own memory, state, and file descriptors. A task is a logically discrete section of computational work. So a process can consist of perhaps one task or perhaps many tasks, depending on the nature of the process. And a thread is the highest level of code that is executed by a processor. And each process has at least one thread. So some more parallel computing terminology. NUMA, an acronym short for non-uniform memory access. It refers to a global address space shared by all cores. Memory is local to each processor, which means it means that, excuse me. Okay. So memory is local to each processor, meaning that larger scale memory is a little bit slower because it needs to be communicated between them. Cache memory is a bit faster, but this is memory that is directly attached to the CPU. These are getting into details that we don't necessarily need to know under most circumstances while using a parallel computer, but it's good to be aware that these things exist. So let's talk about types of HPC computation. We already talked a little bit about serial computing at the very beginning, where a computation runs on one core on one node. Sometimes it's called high throughput computing because you have a lot of data that is going through one particular stream. And again, remember, in serial computing, you only have one stream of instructions that gets executed sequentially, right? And then beyond serial, there's basically two types of parallel computing. We can get a little bit more fine-grained with it later, but for now, we have shared memory or multi-threading parallel computing. This is the case where a single process is broken down into multiple threads on a single node. So the key feature of shared memory parallelization is the shared memory, the fact that it's all on one node. All of the CPUs on that particular node have access to the same RAM or the same memory. So that means they can very easily share data between different processes, and it requires only a very low level coordination. Threads will automatically have access to a shared memory space. Beyond this, we have distributed memory, and the key feature of distributed memory parallelization is that it operates on multiple nodes, and these multiple nodes operate independently. This does require a high level of coordination because of the lack of the automatic shared memory space. So distributed memory means that these processes have to pass messages back and forth over the networking that connects the different nodes. And this is very powerful because it allows you to access a very large number of CPUs for a particular job, but it does also introduce another layer of complexity into the problem. So a few more pieces of terminology here. Massively parallel refers to workloads that use many hundreds or thousands of cores. Embarrassingly parallel is a term used to indicate that a particular problem is completely independent. So it means that, if I'm doing a matrix multiplication, like you see on the screen here, each operation of that matrix multiplication is completely independent. So when I multiply A1 by B1, that doesn't care about the result of A2 times B2, right? So this type of problem will achieve ideal scaling, and that's something we'll talk about soon. Another terminology is MPI, which stands for Message Passing Interface. And MPI is what enables distributed memory computing. So if we go back and look over here, distributed memory computing relies on passing messages over a network. And MPI is what enables that to happen. So MPI is a protocol or a standard defining multi-node communication. And there are a handful of different implementations for it, of which we tend to employ OpenMPI and Intel MPI on our HPC clusters. So some big picture for MPI, you tend to have a process or multiple processes that are managed using the MPI protocol. The MPI protocol is actually implemented by a particular library, such as MPitch or OpenMPI. This is the actual code. MPI itself isn't necessarily a code or a library that you can actually implement. It's just a standard. And then you have different types of MPI implementations that all have their own advantages, disadvantages, use cases, etc. And this allows you, for example, in the case of OpenMP, to take advantage of other libraries such as GCC, Intel, all of these other things that work together to allow you to utilize the message passaging. I keep saying passaging, message passing interface that OpenMP provides to you. So let's talk a little bit about the structure of a CPU, just on a very high level, not into much of a gory detail. So John von Neumann is an important guy to know in the computing world. Many of you probably already know him. He's a Hungarian mathematician, authored the general requirements for electronic computers in 1945, and came up with this idea of the stored program computer that kept both program instructions and data in the memory itself. Prior to this, the program instructions weren't actually kept in the memory of the computer. I'm sure you have this image of the punch cards or these other physical media that would be inserted into the computer in order to provide it instructions. Programming back in the day meant actually physically punching holes in all of these cards, right? That's how the programming was done. It wasn't done directly into the computer. And since then, basically all computers have followed this design. And that leads us into Flynn's taxonomy, which allows us to break down parallelization into different categories. So there are two axes to this diagram that you see here. The left-right axis is the type of data that it has, and the top-bottom axis is the type of instruction that it has. So on the top left, you see single instruction, single stream. Single data, single instruction, single data, which means that as you're running your program, there's only one instruction that's executed at a time, and there's only one data set that it is executed at a time. And there are, of course, many different configurations that you can have within this framework, such as single instruction, multiple data, or multiple instruction, single data. All of these frameworks are supported by multiprocessor computer architectures. And in most cases, MIMD, multiple instruction, multiple data, is how parallelization is done at large scales. And when you're executing programs that have been parallelized, it's good to know how much you expect them to speed up, right? If I have a problem that I'm working on with a single core, and now I'm bumping it up to 16 cores, do I expect it to run in 1/16 the time? Probably not, but these different scaling laws will help us get an approximation or an estimate of the expected theoretical speed up. So Amdahl's law tells us that if a fraction x of a computation is run in serial, then the parallel speedup cannot be more than 1/x. So the idea here is if I have 10 steps to my code and 5 of them can be run in parallel, then I can't have more than a, what is it? That would be a 1/2 speed up because 5 over 10, right? So we'll just go go past this here and talk about these two different types of scaling. So strong scaling, sort of this type of example that we saw in the last slide, was when the total problem size stays fixed as more processors are added. So I'm doing an n by n, maybe let's give it a concrete number. Let's say I'm doing a 10 by 10 matrix multiplication on one processor, and then I want to know how much time it will take if I provide it with 10 processors, for example. The goal is to run the same problems in a faster amount of time. So perfect scaling means the problem is solved in 1 over p as compared to serial. Weak scaling, on the other hand, this is also known as Gustafson scaling. The total problem size per processor stays fixed as more processors are added. So when I double the number of processors I have, that means I'm also doubling the problem size. I'm increasing the data that I'm analyzing, or I'm increasing the number of elements in my simulation. The total problem size is proportional to the number of processors used. The goal is to run a larger problem in the same amount of time. So the goal here is to provide more detailed insights into the system that we're interested in, rather than running a less detailed model faster, right? So as you can imagine, because of this, most research developments are actually made by so-called weak scaling, right? Not sure where the term weak came from in this case. It is a very powerful type of scaling. And we can also see, just to compare these graphs here, the graph on the top shows us that good scaling happens when we are decreasing our time proportional to the number of processors that we have. In the strong scaling case, right? That would be when the total problem size stays fixed. In the weak scaling case, the total amount of time stays the same, and good scaling means that when I double the number of processors and I double the problem size, that I don't actually increase the amount of time taken to resolve. And an example of a case where this scaling problem might be a little difficult, I'm just going to give an example from my own background in astronomical simulations. Every time the process moves forward in one time step, that time step is determined by the smallest resolution element. And you can imagine these volumes as being broken down into resolution elements that are proportional to their densities. So when you have a very small resolution element in the very dense region of the galaxy, this is going to cause a very small time step to take place. The resolution elements further away from the center of the galaxy are going to be much larger because there's less material out there for them to keep track of. In this case, this actually negatively impacts the weak scaling problem, because the number of time steps required to determine the dynamics of the highly dense regions on the inside is actually much larger than the number of time steps that you would need in the less dense regions. So as you're increasing your number of resolution elements, a lot of them are going to go to the higher density regions. So you're going to have more of those problems to solve compared to the less dense ones. So this would actually cause the scaling line to go up, as you see there. There are a handful of different techniques that people have developed to try and improve this problem, but this is just an example of a case where the scaling would not necessarily be perfect. Okay, so basically this is just what I was talking about, is load balance, is when you have some processors that have a lot more work than other processors, right? So the total amount of time to complete a parallel job is limited by the thread that takes the longest to finish. So of course you would want to balance that load more equally across all of the different processors. And here again, load imbalance is caused by non-uniform data distribution. So very high density versus very low density regions. If the space is divided evenly across threads, some threads threads will do very little work, and some threads will do a lot of work. So load balancing is important to consider in your problems. Here we have an example of the different MPI implementations that are available. So depending on which language you're using for your analysis, it's probably going to have its own MPI package or wrapper or library or something like this, right? So Julia, MATLAB, Python all have backends that support MPI to some degree or another. So when talking about parallel computing, it's also important to consider the different types of processors that are available. So CPUs are, generally speaking, a little bit more sophisticated and complex of a processing unit, whereas GPUs are very, very simple. Effectively, they just maximize the number of logical units that they can fit onto a particular chip, which makes it very good for problems that have a very large number of very simple operations to perform. So oftentimes in our analyses, this is the type of chip that will be more effective. So oftentimes in machine learning or in statistics, GPUs are very desirable to have because they provide much more efficient processing. NVIDIA has an elaborate and growing ecosystem based off CUDA, which provides parallel support. So all of these different tools are available to researchers to allow them to take advantage of GPUs without having to do the very low-level GPU programming that's required to program them. So why would you want to use a CPU versus a GPU? So if you're doing sequential code where latency matters, again, for high throughput computing, that might be a case where you would want a CPU. But if you're doing, again, a very large number of very simple operations that are independent, then GPUs are going to be more advantageous. And here's a big list of applications installed on the HPC that rely on GPUs or that can use GPUs. And when you're actually using a GPU, typically algorithms need to be developed in order to do a particular calculation. Developing these parallel algorithms is a little bit beyond the scope of this workshop, but if you'd like to take a more extensive and detailed overview of how this can be done, I recommend checking out this link that's on the bottom of the page here. But for now, we're going to get into practical parallel computing on our HPC. So before we jump into this, I just want to check in with you guys. How are you doing? Do you have any questions? Is there anything to discuss before jumping into the next section? All right, let's get into it. So let's talk about the different use cases of parallelization. So we're going to contrast two different types of user here. So thinking about the research code end user, that's basically all of us. You're going to be an expert in your domain science. So you were trained in biology, or you were trained in physics, or whatever it might be that you're researching. You have some programming experience. Maybe you did some programming in undergraduate. Maybe you did some classes here and there. But overall, programming is, you're not doing research in computer science. You are using computer science to do research in some other field of science. You're interested in producing research insights and writing publications and grants and things like this. Your analysis tends to consist of scripting and using pre-written software packages that were authored by other researchers. So in this case, you need a functional understanding of parallelization to help speed up your analysis and produce your results more quickly and more effectively. On the other hand, we have the research software engineer. Majority of your training might be in computer science, or maybe you have some domain knowledge or experience. This varies quite a lot. Maybe you were a domain expert, but then transitioned more into the development side of things. There's many different pathways to get to here, but the purpose here is that you are interested in developing software. So this is a person who is interested in building and maintaining something like a GitHub repository. And you write and develop parallel algorithms. You're interested in the fine details of scaling laws and memory caching and all of these very detailed things that typical researchers don't tend to worry about. I can't teach you anything. This is not for you. If this is you, maybe we should talk sometime so you can teach me. But this is something that we can do. So what we're aiming at doing here is developing a functional understanding of parallelization to speed up your analysis and produce more results. So let's get into it. So the realities of developing parallel algorithms is that they can be very complicated and they can be very difficult to get right for non-trivial problems. And again, referring to the weak and strong scaling problems that we talked about earlier. And therefore, parallel programs are often developed by specialists, people who think about these problems day in and day out, and tend to get implemented by researchers who don't, I'm saying this for myself as well, don't necessarily know exactly how these algorithms work on the back end. So your typical research workflow would be to develop your research question. I'm interested in studying galaxy formation physics, or I'm interested in processing a trillion genomes, or whatever it might be. You want to determine your data set, and this often is determined pretty directly by your research question. And then the next thing would be to find software that performs your desired analysis. Oftentimes, if I'm doing, I don't know enough about, say, genome science to give a particular example, but if that's something that you're doing, you would find the algorithm that works for you, right? You would download the software, read the documentation again, and then try to, use it to produce the results that you're interested in. So that's implementing it for research. So there might be a few different types of software that you're using. You might be using simulations to generate data using theoretical or empirical principles, or you might be doing analysis software that implements statistical modeling on data that was collected from experiments. So there's a handful of different types of software out there. But what this means is that researchers are often not developing their own high-performance analysis software from scratch. You're using existing models and packages. So research software developers tackle these difficulties on the back end. So there are aspects of parallelization that are not always obvious or well communicated to the people who are using these programs. Many programs need to be told how to run in parallel. Oftentimes, when you're running these programs, it doesn't happen automatically. There's a lot of configuration that needs to go into them in order to make them optimal, or in order to make them take advantage of the parallel capabilities of the HPC. So check your software. What this image here says, we have a Python that is confused by this big multi-node thing. So what I mean here is that some programs are natively parallel. Python sort of being one of them. Effectively, what that means is that if I wrote my code in Python and I send it to the HPC and request, say, 94 CPUs, a whole node, if I haven't done anything particular in Python in order to have it take advantage of the parallelization that I'm requesting in my job, then it's not going to take advantage of that. And you can see that in things like the efficiency report for your job. You might say, oh, well, I gave it 94 CPUs, but it still took just as long to run as it would have on my laptop. I go look at the CPU report, the efficiency report, and I see that, oh, it used 1% CPU efficiency. Well, that's a sign that your program has not fully taken advantage of the parallelization that is available to it. So many programs are not natively parallel. So particularly scripting languages, Python, R, etc., do not automatically have information about the number of processors available, nor how to communicate between them. So there are libraries for Python and R that can take care of this for you. You don't have to do the very low level stuff, but you do at least need to implement things like the R parallel library or the Python multiprocessing library, things like this. So again, implementing proper packages to take advantage of these features. So some general tips for adapting workloads to parallel resources. Oftentimes, you can get away with doing things like meta level parallelization. Say I have a particular algorithm that I want to run on a very large data set. Depending on the nature of what's going on, I might be able to take this data set, chop it into 100 pieces, and then run 100 separate jobs on it in order to do maybe a bunch of different serial jobs rather than trying to come up with a very complicated parallelization scheme to run that algorithm on that whole data set in one fell swoop. So just thinking about nature of your own particular analysis and how you can break down that problem. So shared memory parallelism is also recommended because this avoids internode communication overhead. Basically, what that means is that when you're running distributed memory parallelism, there is some initial overhead in terms of computational cost, in terms of getting these nodes, getting these different components to start talking to each other. So distributed memory parallelism does come into play when you are working on a particularly large problem, or when you have determined that the overhead does not actually outweigh the advantages of using a very large number of cores or memory. So I hope this all makes sense. Just to quickly summarize again, when you're trying to adapt your workload to be parallel, one thing you might consider is a type of parallelization above the job level, where you're breaking things down into many different jobs and then running a large number of jobs at the same time, rather than trying to do one job that does everything. Using shared memory parallelism, i.e. one node or multi-threaded parallelism, avoids this communication overhead. And then if your problem is large enough, then using multi-node parallelism is probably a good idea. So when you're writing or changing parallel code, it's always good to read the documentation and to do your homework to figure out how all of these things are working together. This is going to be highly, highly case dependent, so it's hard to give very general ideas here. So, adapting these things can vary from just changing a line of code here or there. Sometimes it requires a complete algorithm redesign. So again, highly case dependent. If this is something that you're working on and you need assistance, just let us know. Moving on, there are a few other tools that are available on the HPC that can help you. There's HPC Toolkit and there's Valgrind. Both of these are performance metric sort of evaluation softwares that you can use. And so here is a schematic of a multi-threaded program. So we have multiple threads being passed to a particular CPU chip. I guess that's actually a RAM chip. But the idea here is that we are presenting this program with 3 CPUs. You can see in the Slurm directives, it says CPUs per task equals 3. And there are also higher level options such as the OMP num threads. So there are different ways of creating multi-threaded programs. Here's an MPI schematic. So MPI, again, being multi-node communication. So when we're running an MPI program, we need to call this command MPI run and pass it the right arguments in order to make sure that these processes can operate the right way. So each process has an independent memory space, and that's what you can see here on this RAM chip. Each of these processes now is, effectively living on a different section of that chip. And in reality, what this is really going to be doing is there's going to be multiple chips. It's not going to be different spaces on the same chip. It's really going to be each of these processes exists on a completely separate node. So it's on a completely separate piece of hardware. And that's why the communication is necessary. And then we can see that the Slurm directives there down at the bottom are a bit different for this one than they would be for the multi-threaded program. Now let's get into a handful of specific examples that we can use to help increase our utilization of the parallel programming. So the first thing is what I was sort of talking about earlier with this meta level parallelization, where we're able to run many jobs performing similar types of analysis. So that in Slurm, you would maybe want to use something called an array job. So array jobs allow for meta level parallelization. They're useful if you have to run the same analysis on many different data sets and if the order of completion does not matter. So I'm going to use the genome example again, because that tends to be a common case. If I have 100 different genomes and I have one program that I want to run on them, rather than putting them all into the same program, or sorry, into the same job, what I want to do is run an array job where I call the program on each of those data sets and then save the data, save the results independently.
Hey, Ethan, I have a question for you on that.
Sure.
So in that example, how do you optimize and know how to parse or distribute that workload? Like, how do you know how many how many different jobs to run or whatever it might be? Do you have any tools to find out, like to figure that out?
Yeah. So in terms of tools, I'm not so sure. I think this is going to be very case dependent. It depends on the data that you have. It depends on the analysis that you're running. So in the example that I was just using, where you have, say, 100 genomes, and I want to run some pattern matching algorithm on those 100 genomes, then the fact that I have 100 data sets is going to tell me that I want to use 100 array jobs, right? Or maybe one array job with 100 components might be a better way to say that. Does
Okay,
that answer
I
your
just
question?
yeah, I mean yeah, I was just like, how do you know how to divvy it up? Is basically what I was just
Yeah, so
asking.
that's a very case dependent sort of question. So it
Sure,
depends on the type of analysis that you're doing.
sure, makes sense.
Mhm.
Thanks.
Yeah. And so I also want to bring to your attention here, we highly, highly, highly recommend that you use array jobs if you're going to be doing this type of workflow rather than using for loops. So you could imagine, I have data set 1 through 100, and I'm just calling Python my program data set 1 to 100. That might, it might seem like I could use a for loop, write up a quick bash script to S batch all of these different files. Slurm does not like it when you do that, especially for large numbers of jobs. So we highly recommend against using for loops to submit jobs to the cluster. Instead, use array jobs. This is much, much, much better for the scheduler on the back end for it to handle all of these different jobs and to find a place for them to run. So if you have a very small number of jobs, it's probably not going to have a large impact. But if you're submitting hundreds to thousands of jobs, we have seen this. Do not use for loops to submit thousands of jobs to the cluster. This can, under non-ideal circumstances, severely impact the scheduling that goes on. So best practices here, use array jobs when you're running multiple different jobs, especially when those jobs are very similar. Okay, so here's an example of how you might do it. So on the top here, this, I don't know if you can see that. Okay, yeah, so don't do that. That's the for loop thing that I was just talking about. Instead, you want to submit a single batch script, which has this array flag. It could be any number that you want to put here. And then this allows you to use this variable called slurm array task ID. So in this example, you would have input files that are labeled input file 1, input file 2, etc. And then when this command gets run, this slurm array task ID is going to loop through the numbers that you sent it here and replace it with the correct numbers. So rather than doing a for loop, this effectively does the same thing, but in a way that is much friendlier to the scheduler, and in fact, probably a little bit easier on you too, because you only have to submit one batch script. So here would be an example of using MPI on the cluster. So this is an example Slurm script. I've highlighted some of the relevant directives that you see here. So the total number of tasks or the total number of CPUs that we're using in this particular example is 30. We're using 3 nodes and 10 tasks per node. So when I'm running this, I want to make sure to load the modules that are going to be relevant for what I'm doing, say GNU 8 and OpenMPI 3. And then I want to run this program. First, it's getting compiled with MPI-CC. So it's important to note that the compiler is also from the MPI suite. And when the program gets executed, that MPI run command is actually the first thing in that command. And we do -np, stands for number of processes. Slurm tasks, that variable refers to the total number of tasks that are available. So this is going to print hello world 30 times. And I just want to note here, I don't know if I have a pop-up. Okay, yes. So this is just an example. On Puma, you have 94 CPUs available on a single node. So if 30 was the number of processes that you wanted to use, it would still be best to do a multi-threaded single node job for this case. This is just an example that's easy to break down. Those numbers are easy. But you almost never want to use less than the total number of cores available on a particular node, right? If I'm doing a multi-processing job on Puma and I want to use 90 CPUs, there's no reason for me to spread those 90 CPUs across multiple nodes. It's always better. Maybe somebody can think of one odd random case where it might not be better, but almost always it's better to include those jobs, or sorry, those processes on one single node rather than spreading it out if possible. When doing multi-node communication, you want to make sure you're taking advantage of as many processors per node as possible. Okay, I hope this makes sense. So a few other tools, we're going to get into a couple of examples from GNU Parallel and Python multiprocessing. So GNU Parallel is available as a module. So if you want to use GNU Parallel, you'll need to start up an interactive session, do module load parallel, and then you can do something like this example here. So what this example does is just prints out the host name and the date and the processor number. So in this case, we have, we're doing this sequence 1 to 100. And one important thing to point out here is that as you see these numbers go down, 1, 2, 3, 4, 5, 6, 10, this is a little bit out of sequence. So this is something that can happen when doing parallel computations, is that not all of the parallel computations will always execute in the exact order that you would expect them to if they were run on a serial job. So you have this sort of asynchronicity that shows up in parallelization. So here's a couple other examples of using parallel. When I use this command parallel, I'm echoing a number, and I'm using these abcde.txt files as inputs. So when I ran this code, I actually didn't have any files named a.txt, b.txt, etc. It's just the number of inputs that you give there causes Parallel to create that many jobs. And if I wanted to limit the number of jobs to 2, I'm still providing with 5 inputs here, but now I can see that each execution only prints out whether it's job 1 or job 2 by limiting it with the J flag there. And GNU Parallel is very mature software. It's been around for a long time, and there are tons and tons and tons and tons and tons of examples online. If this is something that seems interesting to you, I highly recommend go checking out the examples on the GNU website. But before we wrap it up here, I want to show you some examples with Python, because Python is a very commonly used language, and it's also a commonly misused language when it comes to parallelization. So Python by natively, I guess, is not parallelizable. It is not multi-threaded. So in order to make Python be multi-threaded, we can use a couple of different packages. So the example that we're going to use here is effectively a Monte Carlo simulation that randomly places a point down inside of a square, determines whether it's inside of the circle or outside of the circle, and then uses the ratio of the number of points inside versus outside of the circle to make an estimate for pi. So you can see that math down below the circle on the left there. And then you can see how this is parallelizable by creating a number of different tasks that all do the same thing, and then adding up the number of points at the end. So here's the serial version. We're not going to get super in detail with the code. If you want to look at it, so here's the plot that this is going to generate, but I'll point you to this GitHub. So if you have the slides available with you, you can click that link, or you can type it in order to access all of these codes. So this is an example that you absolutely can run for yourself. I've tested it on the HPC, and here's what you would want to do to run this. So first, you would want to set up your environment. You would want to clone this example, and you would also want to set up a virtual environment to make sure that the proper packages are available for you. So MPI for Pi and multiprocessing. So in this use case, I'm not using Conda. I'm using the Python virtual environment setup, because this is a little bit simpler in order to just get things set up the way we want them to. So we probably don't have time to actually go through this right now, but if you would like to, I definitely recommend just following the directions on these slides and going ahead and giving it a try. So here's how to set up your environment. You want to start an interactive session and then download the example here. And then these .py files are the calculation that's run in serial, a multiprocessing example. So the multiprocessing library in Python enables you to do shared memory parallelism. And just to poll the audience real quick, comprehension check. Shared memory parallelism is that a single node or is that multiple nodes? Feel free to say it out or put it in the chat. Jose says single, that's correct. So the multiprocessing library in Python enables you to access shared memory parallelism, and then the MPI for Pi library enables you to access distributed memory parallelism. And you'll notice that in the MPI for Pi example, you would want to actually start the process with the MPI run command rather than the Python 3 command. So that's an important aspect of this as well. So you can go look at the code. You can go see how that code is written. It's generally pretty simple. This is this is one of the simpler types of things that you can do with parallelization. So I definitely recommend checking those codes out, running them for yourself, and seeing how they work. And with that, here are some resources for R. And again, you'll have access to these slides, so you can go click these links later. And here are my references and some recommended reading. Thank you for listening.
Thanks, Ethan.
Of course. All right, so if you have any questions, I'd be happy to stick around for a few moments to answer them. I do see one from Dave in the chat. It says, just so I understand, not only do you have to configure the Slurm script correctly to run a parallel job, the actual code within the script in whatever language, i.e. Python, must be written to utilize multiple nodes cores, correct? And yes, that is correct. So you need to make sure the parallelization is configured both within the Slurm script and within the code that's actually being run.